All right, we're getting close to the witching hour, so to speak. 3:45, it just turned over, and we are ready to get started again. And leading us off in this last session of the League virtual meeting, getting us ready for the Next Decadal survey, Kelsey Young, the interface between human exploration and lunar decadal science. And Kelsey, take it away.
Thank you, Clive. Okay, so as we heard in the first few presentations today, more so than in the last decadal, we at NASA and in the lunar science community are prepping for the Artemis program, which will put people on the moon in a sustained lunar exploration program. So we on the League Executive Committee thought it was really critical to put forth a paper that demonstrated the value of having humans on the moon in the pursuit of lunar decadal science objectives. All of the co-authors I've listed on this slide were those that signed up for a similar white paper back in October when we had the League meeting, or November. So I've listed all the people who were willing at that time to support a human exploration paper. And if you did not originally sign up, please just feel free to email me and as either a co-author to help with writing or sort of a signatory for this paper, and we'll get you added. But we on the League Executive Committee hope to put this forth also as a League-sponsored paper to again demonstrate the real importance of having humans pursuing lunar decadal science objectives on the lunar surface. So some of the topics to be covered will include what is the value of having crew members in accomplishing decadal science in situ. Of course, this includes putting human brains on the surface of the moon rather than just robotic explorers, and the value that human astronauts have in the discovery and opportunistic science that they'll discover just from being on the surface of the moon themselves. Astronauts are obviously really good at deploying sensitive payloads, and that includes payloads of the ilk that we've heard today in several of the presentations, as well as handheld payloads and instruments that require more constant interaction. The amount of ground covered that a human being can make is substantial, especially with any sort of unpressurized or pressurized rover in the mix. They can complete high priority and especially delicate sampling really, really well. And in the paper, I envision covering topics with references to how humans specifically can accomplish high priority decadal objectives. So a lot of the presentations I've heard today have already called out where humans might be better appropriate to answer some of those questions, and we'll kind of reference those areas where appropriate. And I'd like to try to work with the lead authors of those specific white papers, if you guys are so amenable, to make sure that we're covering that appropriately in this paper. The importance of mobility I intend to cover in this. I see that there's another presentation in a couple from now that I'd like to hear about, and we can cover, to make sure mobility gets covered in one of these white papers or in both if it's appropriate. And I also envision talking about how critical it is to integrate between the science and the human spaceflight communities early and often, including the use of analog field testing. So initial recommendations, I'd like to try to work this with the co-author team, but first and foremost, we want to kind of make sure the decadal accounts for the potential of human exploration, not just kind of purely SMD missions as we're used to them in accomplishing decadal objectives. So what we hope in this paper is that it covers the topics I just described, but it also provides a reference that other white paper authors can use in writing their own white papers to say, hey, point to one really well-referenced white paper in determining the importance of human exploration in accomplishing, any of the variety of the lunar decadal science objectives that we've heard that would benefit from the inclusion of human exploration. So I'm really eager to see the rest of the white paper flash talks in this session, and I'm really happy I think this might be a bit of give and take to make sure we, cover everything in this sort of, league-sponsored, referenceable white paper. So I definitely am eager and open to take feedback from the community and really hope this will represent a wide community effort. Thanks, Clive.
All right, Clive, this is Ryan. Can you hear me?
Yeah, Ryan, we can hear you, but Clive, we can't hear you anymore.
Thanks, Barb.
Ryan, please go ahead.
All right, great. Thanks, Clive. Yeah, so the white paper that I'm going to be leading, a little bit different than some of the others we've heard about in the last few hours. A little bit less science focused, although there is still some science to be done. We'll be looking at how to understand and mitigate plume effects during landings on the lunar surface. So I think probably most, if not all of us, can agree that this is a problem. And for any mission that's going to go back to the moon, this is something that needs to be understood. So we have a kind of a few topics that we're going to cover in this paper. The first off just being the current state of knowledge. So we have several decades worth now of research into this, but there are still significant gaps in our knowledge. So we'll go over like an overview of the phenomenon. Just basically what happens when a rocket lands on the surface, at least as far as we know in terms of dust and erosion rates and things. And obviously one of the big reasons we want to look at this is because of the hardware and environmental impacts, both the ones that are known, for example, from Surveyor 3, and the potential ones for future missions. And we've kind of, between the co-authors and I, we've already been working on a long list of outstanding questions, which you can see some of them here. And I actually didn't have room to fit all of them, but just things like understanding the particle size distribution that's lofted by an exhaust plume. How far do particles travel? How fast do they travel? What directions do they travel? What is the actual density of the dust plume? How do different engine configurations and lander sizes affect plume surface interactions? What are the physical alterations around the landers? And then things like, especially if we're going to land multiple times in the same area, how does that kind of change the dynamics? How do we protect infrastructure? How do plume effects differ in polar regions? Because we know they're going to differ, but how? And then some mitigation techniques, like how important are landing pads or berms or other things that we could develop. So we kind of have a working outline right now. It's going to cover a lot, but really just trying to hit on the importance of understanding this question. And the recommendations we'll put forth are mainly image the descent on every landed mission. Like, it's not that hard. So let's do it. And then we'll go over some other measurements of plume effects that can be done with rovers, lasers, LiDAR, different things that can measure particle velocities and sizes. And we'll kind of briefly hit on things like creating landing pads, getting data from both polar and non-polar regions, et cetera. So if anyone is interested in contributing to this, both in terms of just knowledge or writing, feel free to reach out to me. We'll try to get started writing here in the very near future.
All right, I found the mute button this time, and you still have 3 minutes on your schedule there. So, is there a quick question for Ryan before we move on to the next one? This is a very different topic from what we normally see.
Clive and Ryan, have y'all done any studies here on the S4B stages and lunar module stages that impacted the moon and what they did?
I personally have not. That would be something that I'd probably direct you to Phil Metzger, because if anyone's done it, he has. But I'm not aware of as much work. I know people have identified those locations, but I don't know if they've really looked into the effects that happened there.
Well, that's more of an impact than an exhaust issue.
Yeah.
That's and I know you, Ryan, have looked at the different Apollo sites.
Mm-hmm. Yeah, I've looked at the actual spacecraft landing sites.
Yeah. So, okay. All right. Well, thanks very much. And thanks to Kelsey before you. I was thanking her with my microphone muted. And now that has been fixed. So let's move on then to the next one, where we have Josh Cahill, Lunar Impact Flash and Flux Monitoring for Exploration and Defense, not attack. So.
Yes, thank you. So, there are a few things that kind of broke me out of this static view of the moon in the last several years with LRO, and one was some of the recent impact flashes that occurred, as well as Emerson's paper in Nature, which showed that over the last 10 years of LRO, we have detected over 500 new craters, and of that, at least over 120,000 inferred secondary impacts or modifications of the surface from those impacts. And this is just a fraction of what we know about from LRO. So this has already influenced our understanding of the current impact flux. So we need to basically figure out ways we can increase that understanding with humans and increased activities on the surface to both protect assets and potentially protect people who may be on the surface more readily. So Earth does monitor this in several areas. Atmosphere does tend to be the problem, and it only views one side of the moon. It could be improved with both orbital techniques as well as perhaps techniques on the surface. We're talking about impacts you could potentially detect both from orbit or just on the surface. This may connect with the geophysical network, could also connect with a number of the concerns that Becky Gent was talking about earlier about impact flux. But in general, with the questions that we'll be looking at is what is the current impact flux, both large and small, from large to microscopic? What are the techniques we could do to better understand what those hazards might be, whether they were the initial impact or from secondary impacts, which may be the greater hazard statistically. And what is the distribution of those impactors? Is it completely random as it currently appears, or is there a bit more of a pattern? And how do we go about measuring that? So it'll be pretty basic knowledge for any sustained lunar exploration. When I've talked to previous, say, CLIPS landers or people who plan on doing activities about some of the information that's been coming out of LRO, they kind of raised their eyebrows and like, really? So I don't think this is going to deter anybody from going, but it would probably be best for hazard assessment and plans for accommodation if we had a better idea of what this actually was. So this may influence operations of any landers or robotics, as well as eventual habitats that may be up on the surface, built on the surface of the moon, and how they weather this weather that the moon actually has. So that's it in a nutshell. Happy to have others. We have about 12 to 13 people who I've talked to this point, but we're just getting started, really.
Okay, and again, any quick questions for Josh before we move on? In terms of one question for the map that you show there, Josh, is there any distribution of crater size with a given area, because that would have implications for building a base?
It certainly would. I don't have that information readily. I think we'd have to have a conversation with Emerson regarding that. But yeah, it's a very valid point. So that would be definitely a factor. Okay. It could be that the poles may be one of the safest places on the moon and one of the more interesting places to go right off the bat in that vein. But we don't really have the statistics to back that up. I don't believe.
All right. All right. Thanks very much, Josh. Let's move on to the next one. Georgiana Kramer, are you with us? I take it that's a resounding no, if that's the case. All right. If that is the case, then Esther, are you with us?
Yes, I am, and I'm also taking notes, so I'm going to stop taking notes for a little bit.
Well, you shouldn't need to take notes on the next talk, should you?
No, I will just copy paste from my slide. No.
Okay, just checking, because if you did, then I'd take notes for you.
Oh, okay. Well, you can take notes if you want. I have another person that works with me. Ashley is also helping me out. So
very good.
Anyway,
very good. All right.
So what I'm presenting here is when I attended the league meeting in October, I was selected, or I went to the hazard session, and then I realized that I was sort of a volunteer to work for a paper on the hazards, human hazards versus robotic hazards. And what I did is I also work with Bill Farrell presenting another paper, but then I took this opportunity to work on this other perspective of how important is human missions, so we're going to go anyway, and how do we evaluate these missions and show the value for humans versus robotic, and also what Kelsey was just mentioning before, that it's important to show the value of humans. But what is important also is how do we implement these missions. So what I want to show here, what I wanted to write, or we're writing, is how do we also address the concepts of how humans can help the science from this science perspective. And we provide a concept of operations that is it's integrated, but also helps merge with solving these other SKGs, or the strategic knowledge gaps, help different directorates, which is something that I took as a good, important takeaway from the meeting at League in the fall. And so all of this supposedly is hopefully is going to benefit Artemis missions, and moving on forward to create some stepping stone also for human missions to other planets, obviously from Mars. But I see that this has a lot of overarching with other papers. So maybe if you, I think I'm going to join other authors, maybe Kelsey or maybe some others, and if maybe we can wrap this topic into one instead of dividing so much in little pieces, because that is the mission of having a decadal survey, right? Have a strong papers, white papers. And then I also saw on the spreadsheet that I was that there were also other 2 papers sort of listed there. And so I wrote myself as an author, as a first author for those, but I emailed Barbara and Brett and telling them that I think it's better if we lump all of this together. So maybe I'll have discussions with the other members that are presenting on this session and see how maybe we can collaborate instead of dividing all these important messages, or meaning message that has to go through the decadal survey panelist, and make sure that we have an impact instead of creating different parts. So that's my take. That's it.
Thank you. And any quick questions for Esther, or maybe some not so quick questions? Okay. And you say you've already been in touch with Kelsey?
No, but I will,
Okay.
and I will reach out to her. I have some co-authors on my papers, so I will talk to them and then see how we can merge. So we have other white papers with other people, but I will talk to her, reach out to her, and see how we can combine efforts. Thanks.
Very good.
Yeah, I will. And I'll continue taking notes now. All right. Take care.
Thank you. Thank you.
Uh-huh.
All right. Well, the schedule, for once we are ahead. Is Georgiana Kramer on? George, talk to me. Nope. Then we will move on to the next one. Stephen, Mr. Bailey, I heard you earlier, and I assume you are with us?
I am.
Okay, it's over to you. Thank you.
Thanks, Clive. Greetings. So I wanted to kind of introduce an idea that I think whose time has come, hasn't been talked about a lot, or maybe in just very different contexts. The lunar hopper is not a new idea at all, but the idea that that hopper can be miniaturized to the point to the level where it can be carried around by an astronaut, single astronaut, deployed at will, reused, refueled, and do many sortie missions with many takeoff and landings in between. So things you can imagine this doing is getting to places that would otherwise be inaccessible, like high mountain peaks or the central peaks of prominent craters, or areas that would be hard to cross, like rills, and getting into the rills, getting up close to the stratigraphy in the rills, areas that have very steep slopes, but potential small local landing sites, skylights, and even the interiors of lava tubes. So with a drone, and hopefully you can see the picture there, give you an idea of scale. Think of it as a quadcopter for the moon, or an airless body. So obviously you have to have a propulsion system. But the mass fraction is good. The technology, all of this is just kind of ready to go, with using very conventional propulsion components that have super high heritage and TRL-9 level. We could put something together that would be able to carry sizable payloads up to, if it has a full gross weight of 35 kilograms, it could carry up to 12 kilograms of science payload, can carry 10 kilograms of propellant. And with that, at the full gross weight, it could travel with a full payload back and forth over a 5-kilometer operational radius for a round trip. Fly 5 kilometers away, take off and fly back, and still have some good hover time at the destination. Or with a lighter payload, like 5 kilograms, could travel 20 kilometers in a round trip and return. Or if you wanted to send it on a mission where it was a one-way trip, could go about 160 kilometers in a single direction, land softly, and deliver sizable payload. And that same vehicle, stripped of science equipment and arms and legs and cameras and things they wouldn't need, could actually fly to low lunar orbit. So taking a small payload, about a kilogram, from the surface to low lunar orbit. The level of technology that's available to us now, and the things that have been shown to be operational and have working examples of, allow this thing to operate outside of the direct line of sight, to execute program missions using machine vision, and could really augment both human and robotic missions. So something this light, you could actually take 2, 3, 4, even 5 of these per lander mission, even for a small lander like a CLPS lander. So the landers that have been selected so far in CLPS, this would fit on any of them, and at least 2 and up to 5. So with a vehicle like this, you could deploy David Page's spike penetrators. If they were between 1 pound and, say, 1 kilogram a piece, you could easily have half a dozen or a dozen of the penetrators. You can overfly a big crater like Shackleton and drop probes in as you go.
1 minute, Stephen. 1 minute.
Okay. So it would be powered by batteries, self-charges, it's able to take off and land many times, and can be outfitted with a variety of different equipment so that it could acquire samples and return them. So hopefully you see the utility of a small vehicle like this, and would support this kind of way to greatly expand the ability to extend the reach of humans and get to areas that we otherwise would simply not be able to get to. I'll be happy to take a question or two.
Okay, thank you. I've got one quick comment rather than a question. It seems as if you've got good technology looking for a science reason to exist. I would urge you to reach out to some of the other papers that are out there that are exploring some of these regions, and also include Kelsey and Esther in that particular reaching out. I think there's be some good overlap with what they're up to.
Okay.
Okay.
Thank you.
All right. Let's move on. We'll go on to is it Elisha or Elisha?
It's Elisha.
Elisha. All right. Okay. I almost got it right. All right. An ultra low altitude lunar orbiter. And over to you, Elisha.
Hi, everyone. So today I'm going to be speaking about this mission concept. So it's been clear from the talks today that high resolution data is going to be required for the next decade of lunar exploration. Currently, we have a data resolution gap between orbital datasets and lunar sample studies, and it will be critical to address this gap in the next decade whilst the lunar environment is still pristine, especially with the increasing cadence of planned surface missions. An ultra-low altitude orbiter such as this would be able to advance surface exploration and ISRU beyond LRO for the next decade. So, as we know, many lunar orbiters in the past have collected their most useful data at the end of their lifetime as they're spiraling into the surface of the moon and ultimately crashing. We were thinking about what if this low altitude flight could be extended for the duration of the mission. So many instruments could benefit from ultra low altitude. For example, neutron and gamma ray spectrometers, which have a large field of view, would not be affected by smearing effects at this low in altitude. And this could enable polar ice abundance, resource prospecting, and also another potential payload could be a magnetometer to investigate lunar swirls at very low altitude. This kind of orbiter would be very sustainable and cost effective as it is remaining in orbit and can be targeted to multiple sites. And it will basically be as durable as the amount of fuel that it's given on board. So low altitude orbit has actually already been demonstrated by ESA and JAXA with Earth-based satellites. And on the moon, however, since it is an airless body, the main forces to mitigate at low altitude are gravity perturbations from lunar mascons. So what we've been doing is building an orbital perturbation algorithm using gravity field data from Grail and Lola topography data to basically model the satellite dynamics. The orbiter will use agile thrusters to maintain a minimal eccentricity polar orbit and mitigate these gravity perturbations while avoiding topography as well. So on the plot on the left, I've got a comparison of possible altitudes that a low altitude orbiter could achieve compared with LRO altitude. So this plot is done over the highest point of the lunar surface. This is near Engelgart crater. Just as a comparison, it's around 10 kilometers in height at the highest point. The black line is showing the lunar topography from Lola data, and we've got a red dashed line showing a potential orbit for this low altitude orbiter at a constant 10 kilometers altitude above the surface. And as you can see, it follows the topography. The red band shows potential altitudes that this ultra low orbiter could achieve, so between 5 and 20 kilometers, depending on the topography below it. The blue dashed line is showing LRO's average altitude around 120 kilometers, and the band is just showing the range of altitudes that LRO achieves. And as you can see, with an ultra low altitude orbiter, we are hugging much closer to the surface of the moon, and so we can probe with much higher resolution compared to LRO. The other image that I've got here in the background is actually from the Apollo 17 landing site, and I just thought it would be nice to show how the orbiter would be hugging the topography along its flight path, very low to the surface. So overall, we feel this technology could produce very high resolution data sets with enhanced scientific returns, and we would like to explore this further, possibly in a decadal concept study, and we would like to figure out what kind of science questions it could answer. We would welcome any additional co-authors and signatories, and please let me know if you have any feedback. Thank you.
All right, thank you, Elisha. Let's go to the next talk. This is from a young man by the name of Ron Creel, Power Technologies for Lunar Night Survival and Operation. And over to you, Ron.
Can you hear me, Clive?
Oh, I can hear you, Ron.
Very good. I want to first say, in looking at all the presentations today, Clive and I and Dr. Paul Sputis, watching from some station extraterrestrial, are very pleased that I've seen no times that the moon has not been capitalized. We really want to stress that to the community. Anyway, this is a kind of a follow-on to League 2018 when I presented about lunar night survival. Lunar night covers any time that you don't have solar energy. So it also covers permanently shadowed regions. And also, previously, we only talked survival. I think you need to start getting interested in talk about operation. ALSEPs on the moon, the Apollo Lunar Surface Experiment packages, were only shut off for budgetary reasons back in 1977. They were continuously operating, and we need to have systems that do that. I've tried to show you here the technology readiness levels to revive everybody's thinking about what are the 9 levels. And I've tried to show some candidates that I've been able to discern here. These are all NASA-supported contracts, both SBIRs and what the ESI up there stands for Early Stage Innovations. That's a new project. Those are space grants to universities, as well as game-changing development that they're trying to get. I find very interesting these talks about metal oxidation, metal fuels, and metal oxidation pursuits, and a very interesting acronym, CHIPS, which gets my award for the best acronym. And these systems, even the CHIPS is fed from ongoing work from the universities. That's what the chart tries to show. So basically, you have a range of technology readiness levels that range from 3 to 4 starting out now, except for the radioactive decay, which are the radioisotope thermoelectric generators that were used on Apollo, on the ALSEPs, and also on Curiosity on the moon, and soon to be launched Perseverance rover with a very large multi-mission radioisotope thermoelectric generator. Now, so I've tried to rank here. I don't know on the nuclear fission program, the kilopower, where they really reside on being ready to fly. So this is the type thing. I've got 3 other authors thus far, Matt Kuhns from Maston, Eric Brandon from JPL, and Jonathan Grandidier from JPL that are on there. But we solicit anybody else that might want to join us and to talk about these subjects. There may be other things out there that are being pursued, but I found these are the ones that I could find thus far. And that pretty much sums it up, I think. Looking at my notes, I think I've covered everything. That's it.
Okay, thank you, Ron. We do have time for a quick question. Any questions for Ron? I mean, I have one comment similar to what I said to Stephen earlier on, Ron, is you may want to look at some of those concepts out there that require night survival and operation, and maybe combine with them, or at least overlap with them in what you're trying to do here.
Right. One thing I didn't mention up there, I forgot, was we tried Night Rover Centennial Challenge back in 2011, 2012, and couldn't find any U.S. companies that really had a battery application for that. So the program kind of died. They're now trying to revive it again. It'll start up in September. That's another prize competition I forgot to mention.
Well, there are some private companies that have developed kilopower quite a bit in that intervening time. So that may be something else to think about.
Right,
so,
gotcha.
All right, thank you, Ron. We will go on to the next talk, which is Jonathan Grandidier from JPL, laser power beaming for lunar night and permanently shadowed regions. Jonathan.
Hi, I'm here. Can you hear me?
Oh, yes.
Okay, great. Okay, great. So, so this is a concept of laser power beaming to enable transmission of power without wires. And thanks for the previous introduction from the previous talk. So the objective is to charge a small robotic power system located in permanently shadowed region from a solar-powered lander located at the rim of the crater. And on the bottom right of this box, we can see a concept image showing the rover, which is in the permanently shadowed region of the crater, such as the Shackleton crater. And it received a laser beam from a solar-powered lander at the rim, which itself is exposed to the sun and can generate power and therefore power a laser to beam towards the rover. And we think this might be one of the only way to power a robotic system in the shadowed region. There are other possibilities such as batteries, but or using a tether, but each of them has their limitation either in time or distance. So power beaming, especially in the permanently shadowed region, seems to be one of the only way to provide power to the robotic system. And the other option, which is further term, is to provide power to a base during the lunar night. And here we have this image on the top right showing this orbiter that could be either at the Lagrange point, so in a stationary orbit, and beam power to a receiver during the lunar night. And power beaming has been very has revived recently, and in particular in the Army. So there is we are collaborating for this white paper with NRL, who recently did a demonstration of high power beaming for terrestrial application. You can see a picture here of the demonstration. And we are designing here an end-to-end system which has the emitter, so the laser. So we can see here on the bottom left a block diagram, and the receiver that receives the laser beam for power. And on the right, I tried to put most, if not all, of the main subsystem that compose this power beaming system. And each of these subsystems, we have a representative who is a co-author for the paper. So I'm going to briefly go through them. The laser and the optical element. So here we are assuming 1 kilowatt laser at 1064 nanometer, which seems to be the most appropriate wavelength that could beam for about 15 kilometers, which would correspond to the rim, from the rim to the center of the Shackleton crater, or in a different configuration, beam from orbit at about 65,000 kilometers. Then, since we have a very high power laser, the thermal management needs to be designed and optimized for our case, in particular for space. So we have also a solution for that. And the laser power converter is the element that receives the optical beam and converts it into electricity. So in this case, convert the beam to electricity. And we also have a power electronics, advanced power electronic that converts the energy to either on the rover or on the lander. And so these are all the some of the co-authors that are listed on the bottom of this page. We have some additional co-authors, so the paper is being written right now. I'm expecting to have a good draft by the end of the month, and we also have a lunar scientist. It was pretty hard to find someone available, but who accepted to contribute to the paper and describe some of the application for power beaming on the moon. And one new idea that came was that the laser could also be used to heat some element in the permanently shadowed region, and we could analyze the plume. So that wasn't an expected application, but this is something that came along after discussing with the lunar scientist. So yeah, we were about 10 co-authors, and we are looking forward to complete that white paper and contribute to the LIAG. Okay. So that was it for now. I'm happy to take any questions.
Okay, thank you very much. We've got a discussion period at the end, and we have one more talk to go, unless Georgiana Kramer is here. Still not here. So we'll go on to our last talk, and then we will have the discussion session at the end there, and we go back to Ron Creel, isolation technologies for lunar dust mitigation. And Ron, back to you.
Thank you, sir. Can you hear me? Yep.
Yes.
I always like to check the transmission. Yes, I originally was going to look at a lot of technologies, but honestly, I think I'll tell you the story here that I don't know if we can test here on Earth with the reliability that you need to have for systems to work for the astronauts on the moon. The Apollo astronauts highlighted health and dust management problems on every mission. And this is Gene Cernan's evaluation. He says, I think dust is probably one of our greatest inhibitors to a nominal operation on the moon. I think we can overcome the physiological or physical or mechanical problems except dust. We had planned for the Apollo rovers that I worked on. We had we knew that dust could be a problem. We did special testing at Johnson Space Center using Apollo 12 samples and showed that you could brush the dust away and get back to the original properties as shown in those curves on the right. Here you see an astronaut actually dusting. When the missions were all over, we sat there and we said, gosh, we had the astronauts do too much housekeeping on the moon. And the dust brush didn't work. So Earth testing was not good. Shifting over to item number 3 over there, I found that the folks at Johnson Space Center have done an awful lot of good work on a vehicle that allows you to get rid of the dust concerns. In other words, to isolate yourself, separate yourself from the dust by having suits that you leave outside and that you're able to take a clean suit back inside. The command module pilots repeatedly, when the fellows would come back from the moon and dock with them, they would say, gosh, guys, you got to clean up over there. And there was a cloud of dust and dirt came in there, which is a hazard to the lungs too. And so we need to have clean suits. And that's shown over in the far right on the 4th section over there. That by the way, my helper on this project is Don Barker in Houston, and he added the words there. The best long-term solution includes a lunar dust isolation airlock / mudroom, which you got mudrooms in your house. Some people have, and where you can take off the dirty equipment and keep it isolated from the clean habitat. So the summary down there is that previous testing, Earth-based testing, was very, very difficult, I think, if not impossible, and was not reliable. Isolation from lunar dust is required for successful future moon operations. And we solicit anybody else that wants to contribute here. I know there are a lot of studies out there trying to simulate the lunar simulant and how it performs, but be very, very careful, folks. The moon is a totally different world. Thank you.
All right, thank you, Ron. We are now at the point where we go into the open discussion part for the talks that you've just heard. There were quite a number of different things that were discussed there. There were a couple of dust talks, certainly talking about power. and new technologies that would be enabling for science. Several of these technologies are actually looking for a science question to address. But I think just to sort of reiterate what Jonathan said, he's looking for a lunar scientist. There may be a couple on the line right now that you could solicit and be useful for wrapping into your project, especially those interested in looking into the permanently shadowed craters. So, but open it up for any questions for our speakers so far.
Hi, this is Peter Schipper with a question for Jonathan. My question regards the controls required for accurate pointing of the laser. And I'd like to understand if you've ruled out a phased array antenna and microwave power beaming.
Yes. So that's a great question. I'll start by the microwave consideration, and I think in the context of current research that's being done, and even very near-term demonstration of power beaming from space to Earth in the microwave. I think that in that case it's very relevant because of the atmosphere that would prevent us from beaming in the visible or near infrared. But on the moon, we don't have any atmospheric issues, and there is some significant advantage into going to visible or near infrared, and that's because the divergence of the beam is proportional to the wavelength, meaning that if you have a short wavelength, you can have a very narrow beam and focus the power into your laser beam without having it diverge like you would have for microwave. So that's my answer in if we consider microwave. So yeah, we've looked into that, and the choice of going to 1064 or visible wavelengths was motivated by this. And the other question, I think you were asking about phased array. So right now we are looking at a single fiber laser, and that's because the primary application is the permanently shadowed region. We think this is what we can do in the near term, in the next 5 to 8 years. And for a kilowatt class laser, a single fiber laser would be sufficient, and we probably wouldn't need a phased array to have several lasers and increase the power. So I hope that answered the question.
Thank you. Yes.
Okay. Other questions, please.
This is Peter Schipper with a question for Ron about the dust mitigation. I'd seen some work on people using electrostatics for dust mitigation, both for preventing it from coming in the first place because it's usually charged, and also even for moving it off of a surface so that we don't have the astronauts doing that. Can you speak about electrostatic mitigation for dust?
My only response would be, that may work here on Earth, but will it work on the moon? And that's a heck of a place to be doing experiments up there with some wand that you swipe over the surface. And really, think about the time that we spent in trying to clean yourself. If you had a suit that you could remove, you just leave it outside. You don't have to clean it. You have a clean suit underneath, which you can readily now wear into the clean habitat.
Okay. So anything else for this session or any other session that we've heard today? It's a lot of applicabilities and maybe some connections that need to be made by various white papers, at least that I've heard today. The one thing that I will say, my observation is that there's a tremendous amount of unanswered questions to be answered on the moon. that informs solar system science. And that comes from the actual number of papers that are actually on the spreadsheet and have been presented here today. So hopefully there are more questions.
Clive, this is Peter Shipper with a question for you. How can we get a nuclear reactor on the moon?
How can we get a nuclear reactor on the moon? Well, I think
how can we use this forum to make the pressure so that, because everybody knows that we need to have that steady power day and night. It would be so helpful to have that. We all want it, but how can we work together to push that forward for this decadal survey?
Well, for this decadal survey, I think we need to show a need for killer power, killer power. So I think that I don't see any application so far that the science would justify. But if we then start looking at the more applied side, the exploration side, for example, the science of in situ resource utilization, we know that that's one that's power hungry and would require killer power. So I'm not convinced that a decadal survey is the route to push for killer power on the surface, but I think that's going to happen and we can take advantage of it. So, okay. All right. So if there are no more questions.
Hey, Clive, this is Carolyn Crow.
Hello.
Hey. So I just had an observation. One of the technologies that wasn't really covered, and that's really relevant to a lot of talks that we saw earlier today, is laboratories for analyses of return samples. And I'm just curious if that warrants its own white paper, or if there are plans to include that in more of an overview from League, or what your thoughts are on
that. My thoughts
Carolyn,
on that.
Carolyn, this is Barbara. CAPTEM is writing papers on this topic.
Okay.
It seems like something that would be a really good crossover paper between lunar scientists and other sample scientists, especially given the National Academy's report that came out, I don't know, a year or two ago, and doesn't seem to have gotten a lot of traction at NASA.
So is that something we should kind of, punt to CAPTEM, or do we want to try and...
I don't think we can afford to punt anything. I think if you're interested in it, we've got to make it happen.
Yeah.
That can be as simple as getting on an email and starting some discussion and making sure there is a paper available, and then maybe contributing some lunar science to it.
Comment?
Yeah.
This is something that we will take up in the South Palakan Basin Sample Return white paper, but it would be great to have a white paper just on this topic, and I think you'd find a lot of support for that, and could be cross-referenced. I think it'd be very powerful.
Yeah, I'd certainly be very in favor of this. Remember that the National Academies did have a study to look at sample return facilities and sample and funding of lab facilities outside of the NASA system. Those recommendations were presented to, it was requested by Jim Green when he was AA for the Planetary Science Division, and that report has been received, but the recommendations have not yet been followed.
And that report doesn't necessarily get, included into the decadal survey unless we put it into a white paper, correct?
It would be good to reference that as at least as a point of departure, because that was the latest work that's been done on it.
That's actually a really good idea. I mean, we could sort of take some findings from that report and some of these things that we've heard that really would benefit from lab analysis, and maybe propose a page or two to the CAPTEM folks and see if we can join forces with other lab people.
Sounds to me like we have a volunteer. I'm just saying. No good deed goes unpunished, Carolyn.
I can look into that, especially since I'm on CAPTEM. So.
Yes, thank you.
You're welcome.
But if you need any help, I will certainly be willing to help out where I can.
Okay, great, thanks.
I'm going to pass it back to Barbara and Sam if he's still on.